All right, here we have a classic ladder problem. This is the ladder right here, leaning up against a wall. This is the wall. Again, a ladder. There's the wall. Here's the ground. Here's the happy person standing right here on the ladder. So I've already solved this for you, but I want to walk you through it. So the free body diagram, you've got the wall pushing on the ladder to the left. That's FW, the force of the wall. You've got the normal force, which is the force of the floor pushing up on the bottom of the ladder. And of course you have static friction pushing in on it so that it doesn't slip. The ladder makes an angle of 65 degrees with the horizontal. This is the weight of the ladder, what I've labeled as FGL, straight down through the middle of the ladder. And then this is the weight of the person, FGP, gravitational force of person, going down here. All right, so the mass of the ladder is 25 kilograms. The length of the ladder is 7 meters. The mass of the person is 78 kilograms. And the person is 5 meters up the ladder, measured from down here up to there, 5 meters. The goal is to find the coefficient of static friction between the ground and the ladder, the coefficient. So to find that, of course, we need to know the normal force, which we can find in the y-axis, and then the static friction, which we can find in the x-axis. Static friction, because this is all in equilibrium, static friction will equal the force of the wall, and the normal force will equal the sum of the weights in the y-axis. So starting in the y-axis, here we have, in the y-axis, it's in equilibrium, so the net force in the y-axis equals 0, normal force is up, and the two weights are down. So normal force is up and the two weights are down. So that adds up to 1,009 newtons, right there. Okay, now to find the force of the wall, well, I've got three unknowns. Well, actually, no, I have two unknowns now because I know the normal force, right? But I still have two other unknowns, the force of the wall and the static friction. Well, obviously, how am I going to find that? I am going to have to use torque, and I'm going to have to define my lever arm so that I can get rid of one of the unknowns. Now, I could do this and go straight to the static friction, but I find it easier to make this, to make the bottom of the ladder the axis of rotation. So that's what I'm going to do. I find it much easier to do that. So net torque is 0. The counterclockwise, of course, the net counterclockwise torque, CCW counterclockwise, equals the net clockwise torque. Well, what is the net counterclockwise torque? Look at these forces. The force that is pushing, that would make this whole system rotate counterclockwise around the axis of rotation at the bottom. The only one doing that is this one, the force of the wall. The normal force acts through the axis of rotation, no torque. Static friction acts through the axis of rotation, no torque. The only one that is counterclockwise is the wall. So there's the torque of the wall, which is the force of the wall times the length from the bottom up to there, times the lever arm, which would be the sine of that angle. All right. How do I get the lever arm to be the sine of the angle? Well, that's a good question. Let's change colors. Let's go to green. Whoopsies. So the lever arm, here's the axis of, there's this line of action for that force. The lever arm, remember, is that line that goes from the axis of rotation to the line of action at right angles. Notice that, well, if that's 65 degrees, then that's 65 degrees. And so that's the angle that is right here. Okay. Now, on the other side, you've got the torque due to the weights. And notice that the weights are down this way, okay? And so these around this point right here would make it go clockwise, okay? Look at the direction they're going. They would produce a clockwise torque. So that's why they're on the other side here. The torque due to the ladder itself, which acts through the center of mass of the ladder, and the torque due to the person, which is this one right here, okay? Well, the ladder itself, is the force of the ladder right there is the weight of the ladder times what I called LL, which is at 3.5, because remember, it's halfway along. The ladder is 7 meters long, so half of 7 is 3.5, because it acts midway, at the midway point. All right, times the sine of 25 degrees. The reason why I use 25 degrees, you could have also used cosine of 65. I used 25 because if that's 65 right here, then this is 25. And my axis of rotation is right there. Okay? Let me get rid of this right here. So my axis of, not my axis of rotation, my line of action is right here. And that's a 25-degree angle. For the other person, for the person, the angle, the 25-degree angle is right there. And its line of action, sorry, it's the lever arm is right here. Okay, remember what lever arm is from the axis of rotation to the line of action at 90 degrees. Okay, so I've got the weight of the person. Let's get this. Okay, the weight of the person right here times the 5 meters. They're 5 meters up at 25 degrees. Doing all this math, I end up with 312 newtons as the force of the wall. So that's the force of the wall pushing to the left right here. So that equals the static friction. So let's go down here and finish this up. So the static friction equals the force of the wall. In the x-axis, net force is 0. Static friction equals the force of the wall, which is 312. All right, it's 312 because that's 312, right? Now we can go, since we know the static friction is 312 newtons, that's right here. So that equals mu times the normal force. Solve for mu, and so mu is greater than or equal to static friction over the normal force. Put in the numbers here. Remember the normal force we calculated in the y-axis. Here's our static friction, and we get an answer of 0.31. So it is at least, the coefficient of static friction is at least 0.31. It could be greater, but it's at least 0.31, and that's our answer.